Hey guys, so this is our video on phases of matter and different forms of matter. You're going to learn about something called allotropes, which I have to tell you right now is one of those things that when it comes back to the Regents in June, everybody forgets that they even existed. So I'm going to spend a little time on it, hoping that it sticks with you. Before you begin watching, I kind of have to preface this with an apology because when I first recorded this, I had my mic on, but my camera was off. So this is going to be an audio only video. Here we go. Make sure you got your notes. Let's learn about phases of matter and allotropes. Alrighty, so let's talk a little bit about some of the phases that elements are found in, because there's, well, three main phases. You probably know them: solids, liquids, and gases. But we have different elements that appear at what we call standard temperature and pressure, which is 0 degrees Celsius and a pressure of 1 atmosphere, in distinct phases. So the first phase we're going to talk about is solids, because most of the elements out there are solids. In fact, most of the elements on the periodic table are actually metals, and most metals are solids at standard temperature and pressure. There are a few exceptions, and we're going to get to those. So some examples of solids would be things like copper, which is symbol Cu, iron, which is symbol Fe for ferrum or ferric, and gold, like I used before, which is symbol Au. Now, we also have a bunch of gases. 11 elements are gases at standard temperature and pressure, or STP. You might see it referred to as that. Examples of these are neon, Ne, nitrogen, N, oxygen, O. In fact, our gases comprise everything in group 18 on the periodic table, the noble gases, and a portion of the elements in groups 15, 16, and 17. And that's something we're going to go into in a little bit more detail. We only have two naturally occurring liquids on the periodic table. One of them is a metal, one of them is a non-metal. You've probably heard of the liquid metallic element, and that would be mercury. The other one is bromine. Bromine is our non-metal that is a liquid at standard temperature and pressure. So let's talk a little bit about monoatomic versus diatomic elements. So the prefix mono generally means what? Well, it means one. You might have heard mono a mono, which means one on one. Okay, so monoatomic means one. Di, on the other hand, means two. So some elements are monoatomic, which literally means one atom, and other elements are diatomic, which literally means two atoms. So most atoms are monoatomic, which means they exist singularly or alone when they are in their unbonded state, when they are pure. However, some elements are diatomic, and these are going to be really important for us to remember. It influences a whole bunch of things about how they react, and for some of them, how they don't. Diatomic means that they exist bonded to another atom of themselves when they are in their pure state. Now, the classic example for that is O2. And let me just turn on my pen. So you've probably seen oxygen written like that before. If you haven't, that's okay. O2 literally means there are two oxygens, and that's because oxygen is diatomic. Now, there are certain elements which are our diatomic elements, and they include bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These 7 elements will always exist bonded to another copy of themselves if they are not bonded to something else. So that means you will never see, for example, iodine just written as I. unless it's bonded to something else. You will always see it as I2. You'll never see chlorine written on its own either. It can't exist on its own because it's diatomic. It'll be Cl2 if it's not bonded to something else. Now, I'm going to point out that very common compound, which you've probably seen before, is NaCl, sodium chloride, also known to you as table salt. If you look here, you'll notice we have no subscript, that's what this little 2 is called, beside our chlorine. And that's because the chlorine is bonded to something else. So it doesn't have to bond to another copy of itself by default. Just want to put that out there right from the beginning. So we also have something called allotropes. Allotropes are kind of crazy. They're different versions of the same element that because they're different versions of the elements, they behave in very different ways. And I'm going to go into that in a little more detail. So an allotrope is defined as a different form of the same element in the same phase, which means we have to be talking about solid and solid, or liquid and liquid, or gas and gas. Because they have a new formula, they will have new properties. If you remember back in living environment, one of the things you learned about was enzymes. If you change the formula of an enzyme, you change its function. If you change its shape, you change its function. With allotropes, if we have a new formula for an element, it will have new properties. I'm going to show you some examples of those. Classic example is O2 and O3. O2 is the oxygen that we breathe, diatomic oxygen. O3, on the other hand, is ozone. Ozone is produced when oxygen is exposed to a very strong electrical field. That's why you sometimes, I don't know if you've ever noticed this, but if you go outside just before a thunderstorm, sometimes you can smell the ozone. And that's because in the upper layer of the stratosphere, you have electrical strikes or lightning strikes happening. It also occupies, you probably heard of the ozone layer, okay, that helps to shield the Earth's surface from ultraviolet radiation. Another example would be phosphorus. Phosphorus exists in a couple of different forms, so does carbon, and we're going to take a look at some of those now. There are 3 main allotropes of carbon. The first one is graphite, the second one is diamonds, and the third one is Buckminster fullerene, which is its own whole category of stuff. In graphite, each of these little spheres are a carbon atom. But if you look, they're arranged very differently in graphite than they are in diamond. And those are arranged very differently from what they are in Buckminster fullerene. So the thing to remember is the way we arrange those atoms and the way they are attached to one another affects how they behave and affects how they function. So graphite, if you look at it, the way the carbon atoms are arranged are in very flat sheets. This allows graphite particles to slide over one another. Graphite is very commonly used as a dry oil. For example, if you have, say, the key in the lock on your front door is sticking, a locksmith might spray graphite powder into that lock. It's perfectly dry, but it'll allow the lock parts to slide past one another, just the same as if you had pumped that lock full of oil. Okay, graphite also happens to be what's actually in your pencil leads. There's no lead in a pencil lead, it's graphite. And the fact that those flat sheets of carbon are stacked on top of each other, when you write with a pencil, the graphite is literally slipping off the top of that column of carbon. So graphite is in flat sheets. Diamonds, on the other hand, are arranged in a crystal lattice structure that creates a very hard defined arrangement of carbon atoms. You probably know that diamonds are one of the hardest substances on Earth. They're hard in terms of scratching, but you can crush or destroy a diamond if you try just a little bit. It's not even that hard. Their strength comes in terms of marability. So diamonds form this very regular crystal structure that allows them to be perfectly clear in a pure diamond when light is shown through them. That's what we classically think of as a pretty diamond. Now, our other allotropes of carbon include all the classified groups of Buckminster fullerenes. You might also see these referred to as buckyballs or bucky tubes. These are chemically produced. They were discovered by a man named Buckminster Fuller, hence the name. And they kind of look like soccer balls, or they can look like a globe arrangement. Depending on the way that the atoms are arranged, it will determine their shape and their function. So you can have things like these Buckminster fullerene balls, and these are used in nanotechnology to deliver medication or to deliver a charge within a structure. But you can also have these things like that are nanotubes that can be used to literally build things on a molecular scale. So these are all different allotropes of carbon. We've got graphite, you can see here under B, a bunch of different Buckminster fullerenes, diamond, and also a nanotube. Another classic example of an allotrope, and then I'm going to finish with those for now, is phosphorus, P4 versus P3. So there are two allotropic forms. If you have P4, that's your white phosphorus, and it spontaneously ignites. It's incredibly unstable. It will literally explode if you look at it the wrong way. Red phosphorus, on the other hand, is the type of phosphorus that's used in matches. So obviously it's more stable. You have to apply a force to it in order to ignite it. So let's talk a little bit about compounds. Compounds are whenever you have two or more elements that are chemically combined in definite proportions by mass. We also consider compounds to be pure substances. And you might think, well, Miss Knoll, how can it be a pure substance if you're combining elements? You said elements were pure substances. How does this work? Well, because we've chemically combined them, they are now pure on their own. For example, H2O, water. If all you have in it is H2 and O chemically bonded together, which is hydrogen and oxygen, in the proportions of 2 hydrogens for every oxygen, you end up with a pure substance. In this case, it would be pure water. A molecule is defined as a compound that is bonded with a covalent bond. This is something that's going to be very important to us when we get to bonding. A formula unit is a compound that is bonded with an ionic bond. And we're going to talk more about those when we get into bonding. But let's tie this up with a little bit on the law of definite proportions. The law of definite proportions says the types of atoms in a compound exist in a fixed ratio. For example, water can be decomposed or broken down into the hydrogen and oxygen that make it up in a fixed ratio of 1 to 8 by mass or 2 to 1 by moles. It will always decompose into this ratio because of the way the atoms proportionally combine. We will always have 2 hydrogens and 1 oxygen to make our water. That gives us a ratio of 2 atoms of hydrogen to 1 atom of water. And if you notice, this subscript tells us that ratio. Here we have a 2, here we have nothing. If you don't see a subscript, it's assumed the subscript is 1, even if we don't show it. So, are each of these elements or compounds? Let's try them and then we'll go over them. So A, chlorine, is that an element or a compound? Well, that, my friend, that's an element. It's one element, nothing else is shown. What about B? Well, that's water. H2O, 2 elements bonded together, that's a compound. What about C? Well, here we have calcium, carbon, and oxygen. That would be a compound. And what about D? CO. This is a tricky one. This is just an element. Remember, our rule is that the elements have to start with a uppercase letter. If you have a lowercase letter after an uppercase letter, That means that that is all one element, that is CO, also known as cobalt. Now, example 5. Which of these can be decomposed by a chemical change? So remember our definitions. Elements cannot be decomposed by a chemical change, and compounds can. Take a moment and tell me for each of these which ones can be decomposed by a chemical change. So if you said A, that can be decomposed because it's a compound. B cannot be decomposed by a chemical change because that's an element. C, we have two elements here, they're bonded together. This is ammonia. That can be decomposed by a chemical change. D, that's our calcium carbonate again. That is a compound. That can be decomposed by a chemical change. And then lastly, E, that's good old neon. That's a single element that cannot be decomposed by a chemical change. Remember that in a compound, the ratio of elements matters, not just the presence of the elements. If I have H2O, well, that's water. If you're thirsty on a hot day, that's going to be a refreshing, wonderful drink. On the other hand, H2O2, that's something totally different. This is a compound you might have in your house, in your medicine cabinet. Hydrogen peroxide. Well, you go to drink hydrogen peroxide, specifically if it's pure, well, you just won yourself a trip to the ER and maybe even worse, okay? The components of these are the same, but because the ratio is different, they are different compounds and thus have different properties. That's it for our second lesson on matter. We talked about elements, we talked about compounds, we learned about monoatomic and diatomic elements. We looked at how many different elements are in different compounds, and we also learned about allotropes, which are different forms of an element based on different chemical formulas and arrangements of atoms in those elements. That's it. Have a great day.